This is GUT modules number 3. We'll talk about water, pH, and buffers here. This is just basic chemistry again. Introduction, what are the ionic properties of water? What is pH and what is pKa? How do amino acids change with changes in pH? What is a buffer? What is an isoelectric point or PI? Remember that water, oxygen and 2 hydrogens, H2O, has a dipole moment, so the oxygen's slightly negative charge and the hydrogen's a slightly positive charge. There are hydrogen bonds or proton sharing, especially between nitrogens and hydroxyl groups. Non-covalent bonds, or they're weaker bonds, are only about 1 to 5 kcals per mole. Covalent chemical bonding has shared electrons, substantial bond energies as enthalpies. Single bonds have an enthalpy of 50 to 100 kcals per mole. Double bonds are 120 to 170 kcals per mole, and triple bonds are about 195 kcals per mole. This is the water ionization. Water does ionize, and you can write an equilibrium constant for that. The sum of the products of the ions divided by the concentration of the water. But since water is essentially constant relative to the size of these other hydrogens and hydroxyl groups, we write a Kw, and Kw is just the product of the protons times the hydroxyl groups. And that Kw is equal to 10 to the minus 14, and pH equals negative log of the hydrogen ion concentration. So each unit on the scale of 0 to 14 represents a 10-fold difference in proton concentration. Neutrality exists at pH 7 because hydrogen ions, protons, equal hydroxyl ions at pH 7. So here is a schematic showing you the relative concentration of hydrogen ions compared to distilled water. 10 million, 1 million, 100,000, 10,000, 1,000, 100, 10, and 1 at pH 7. And then the reverse goes into the case very few protons down here at pH 14. Acids and bases, simple acids such as acetic acid will ionize to its conjugate base, then giving up a proton. So acids are proton donors. Bases are proton acceptors. So is ammonia. The ammonia gas will dissolve in water and bind a proton, and that forms an ammonium ion. And so this is a base because it's accepted a proton. Henderson Hasselbalch equation reads the pH equals the pKa plus the log of the proton acceptor divided by the proton donor species in molar ratio. So pH equals pKa plus the log of base over acid, where A is when A equals HA, pH equals pKa, because when A equals HA, then this term, the log of 1, is 0. Ionizable groups are half protonated, and so at the pKa, the ionizable groups are half protonated, half this and half that. Isoelectric point, or PI. The pH at which the net charge on a molecule is 0 is the isoelectric point, or PI. Draw out the titration curve. pH versus equivalence of base start with a molecule fully protonated. When 0 is between 2 pKa's, just average the 2 pKa values. If the PI is not between the 2 pKa's, use the Henderson Hasselbalch equation. And note that this molecule is charged, but that the net charge is 0, so there's a -1 here and a +1 there. The weak acids, so we have a weak acid, acetic acid, ionizing to acetate here, and that gives up. So hydroxyl group comes in, takes off a proton there, and that proton goes out to form water, mixes with a hydroxyl group to form water. And so this is the red region is the highest buffering capacity. Below that, changing the concentration, adding more equivalence of hydroxyl group changes the pH pretty dramatically, but pH doesn't change much in this region because we're getting buffering capacity here. And then finally, once it's all the reaction has taken place, all the protons are gone, then we can the buffering pH changes then a lot. Titration of amino acid. Form 1 is fully protonated. Form 2 is net zero charge form. Here we got a negative charge and a positive charge. This is the fully protonated form with a positive charge on it. And then form 3 is a totally unprotonated conjugated base form. So here is the base form, but it's ready to accept protons. It'll accept a proton here and a proton here coming back in this direction. Has 2 regions of buffering capacity. The pI is right here at 5.7, halfway between the 2 pKa's. Just average those, 9.1 and 2.3, and you got the pKa. And here's the amino acid tyrosine being ionized. So here's it has several equilibria: 4 for the first carboxyl group, 8 for the amino group, and then 10 for the phenolic OH group. Out here is the last thing to come off. Gives species D is fully unprotonated. Species A is fully protonated. Net at pH 6, the net charge is 0. So net charge is 0 here. 1 negative charge, 1 positive charge. pH 9, net charge is -1. So, and the pKa is 8 for this change here, 10 for there, and 4. So it has 3 pKa's, 4 different species. So we can look at this, the titration of tyrosine. We can draw a titration curve going from positive charged, then to through this pKa at 4, then 0 occurs somewhere in here between the 2 pKa's. So you can just average those pKa's, 8 and 4, divide that by 2, divide 12 by 2, and you get 6, so the pI is 6. What percentage of histidine amino acid side chains are uncharged at pH 7.5? The pKa of histidine is 6.5. The Henderson Hasselbalch equation must be used to solve this problem. pH equals pKa plus the log of His 0 over His positive. So this is protonated form, and this is the basic form, the conjugate base that it will accept a proton. So pH 7.5 equals pH 6 equals 6.5. Plus the log of His 0 over His plus. So the log of His 0 over His plus equals 1. His 0 over His plus is 10 to 1. The anti-log of 1 is 10 to 1, or about 90% is His 0 when it is in this at pH 7.5, so it's 1 pH unit above the pKa. You'd expect it to be almost fully unprotonated, and it is 90% unprotonated, as you would expect. So you can logically think this out as well as calculate it. Carbonic anhydrase, CO2, is an extremely important molecule in the body because we make lots of it in metabolism. It combines with water to make carbonic acid. The enzyme carbonic anhydrase that's found in the red blood cells catalyzes this reaction, so it's just not CO2 dissolved in the blood as you would have in a soda pop, but it's reacted to form carbonic acid. That carbonic acid then ionizes to yield bicarbonate, principal base form in the blood, plus a proton. And you could write out a pKa for this, a Henderson Hasselbalch equation for it. pH equals pKa plus the log of the proton acceptor over the proton donor, which actually is 2 species, CO2 and carbonic acid. And this has a pKa of 6.1, so it buffers very good against acid, but not very good against base. CO2 is a volatile anhydrous acid, so because this can be exhaled, this can shift this whole reaction back to the left and keep the acid, get acid out of our bodies. As you do that, you'll take protons out and change the pH of the blood. So here's a red blood cell with CO2 from metabolism going in. Carbonic anhydrase acts on it to make carbonic acid. That carbonic acid then ionizes with water to make bicarbonate and a proton. The proton can then bind to hemoglobin. That causes the hemoglobin to release oxygen more readily. Hemoglobin comes off. The bicarbonate goes out into the blood. To maintain neutrality, chloride comes back in, and that's called a chloride shift. So it has an anion exchanger that does this bit right there inside in the wall of the red blood cell. So the pH is important. In the stomach, aspirin is protonated and uncharged, so it enters the blood quickly. Enteric-coated aspirin enters the blood slowly in the intestine, which is alkaline because it is charged. So in the stomach, at pH 1.5, aspirin is quickly absorbed, and in the intestines is more slowly absorbed. So if you're having a heart attack and you need to get aspirin in a hurry, you don't want to take enteric-coated aspirin. You want to chew up an aspirin so it dissolves very quickly in your stomach and it gets into your blood to deactivate your platelets a bit and therefore slow the clotting process. So drug absorption. If you're and this is the example of aspirin here in the stomach with the acid pH, it absorbs quite well, and that's because if it's uncharged, it goes through the bilayer of the membrane of the stomach and gets into the blood. And this is a picture of Mount LeConte at sunset. I made this back in 1979, right after coming to Quillen College of Medicine. Hope you enjoyed this very short video, and it's